Welcome to Earthly Teachings. In this video, we'll be tackling a summative assessment on Electrotechnics N4, focusing specifically on transformers. We'll be working through a series of questions, covering both theoretical and practical aspects, which is perfect for South African N4 students preparing for exams. Our goal is to provide clear, step-by-step explanations, so by the end of this tutorial, you'll be able to confidently answer similar questions in your assessments. Let's begin with our first question, worth 3 marks. Question 1 asks us to briefly explain the construction of a transformer. The fundamental construction of a transformer consists of a laminated steel core and 2 windings. You have a primary winding, which is connected to the AC supply, and a secondary winding, which is connected to the load. These 2 windings are insulated from the core and from each other. They are wrapped around the common laminated steel core. This means that while the windings are physically close, there is no electrical connection between them. The core provides the pathway for the magnetic flux. Question 2 asks for our understanding of mutual inductance. Mutual inductance is a phenomenon where a change in current in one coil induces an electromotive force, or EMF, in an adjacent coil. This is a direct application of Faraday's law of induction. The magnetic flux produced by the first coil links with the second coil. When we apply an alternating current to the primary winding, it creates an alternating magnetic field. This field is channeled through the steel core. This alternating flux then cuts the turns of the secondary winding, inducing an EMF and consequently a current if the circuit is closed. This is the very principle on which a transformer works. Question 3 asks about the adverse effects of eddy currents. Eddy currents are small, localized circulating currents induced within the transformer's iron core by the changing magnetic flux. Because the core itself is a conductor, it experiences the same induction principle as the windings. These currents, however, do not flow through the useful turns of the coil. The first major adverse effect is heating. Eddy currents flow against the electrical resistance of the core material, converting electrical energy into heat. This is a waste of energy and can cause the transformer to overheat. The second effect is that these eddy currents produce their own magnetic fields, which, by Lenz's law, oppose the main magnetic flux. This parasitic magnetic field reduces the effective magnetic flux that links the windings, which reduces the transformer's efficiency. Question 4 asks for the meaning of laminating the core. Laminating the core is a technique used to overcome the problem of eddy currents we just discussed. It involves constructing the transformer's core not from a solid block of iron, but from a stack of thin sheets of silicon steel called laminations. Each of these thin laminations is coated with an electrical insulating material, like varnish or a thin oxide layer. They are then tightly stacked and bolted together to form the core. Visualization of a laminated core, a stack of thin insulated sheets. This insulation between the sheets prevents the large circulating eddy currents from forming. Instead, only tiny localized eddy currents can exist within each individual lamination. Because the path for these currents is so small and their resistance is high, the overall eddy current loss is dramatically reduced. This improves efficiency and prevents overheating. Question 5 asks about forced air cooling. Forced air cooling is a method used to dissipate heat from large transformers, which generate significant heat due to losses. In this method, the transformer's radiating surfaces, such as its tanks and radiators, are cooled by a blast of air from external fans. Unlike natural air cooling, which relies on convection, forced air cooling uses fans to actively move a large volume of air across the hot surfaces. This significantly increases the rate of heat transfer, allowing the transformer to operate at a lower temperature and higher efficiency. We now move to a couple of quick fact-based questions, perfect for 1 or 2 marks. First, question 6. To which part of the transformer is the breather attached? The answer is the conservator tank. The breather ensures that the air entering the conservator is free of moisture. Next, question 7 asks for the color of silica gel. Before absorbing moisture, it is typically blue. After absorbing moisture, the silica gel in the breather changes color, usually to pink. This serves as a visual indicator that the gel is saturated and needs to be replaced or regenerated. Question 8 asks for the function of the Buchholz relay. The Buchholz relay is a gas-actuated protective device, primarily used on large oil-immersed transformers equipped with a conservator tank. Its main function is to detect and provide protection against most internal faults that can occur inside the transformer tank. These faults, such as insulation breakdown or core faults, generate gases and cause oil movement. It's a two-stage device that detects these internal problems. Depending on the severity of the fault, it will either trigger an alarm or completely trip the circuit breaker, disconnecting the transformer from the supply to prevent further damage. Question 9 delves into how the Buchholz relay operates under two specific fault conditions: overload and short circuit. Let's start with overload. An overload means the transformer is being asked to supply more power than it's designed for. This excessive current leads to significant heating of the windings and the transformer oil. This overheating of the oil causes a slow decomposition of the insulating materials, producing small combustible gases. These gases are lighter than the oil and rise through the pipe towards the conservator, where the Buchholz relay is located. As these gas bubbles accumulate in the upper part of the relay, they displace the oil. The oil level inside the relay drops, causing the upper float to pivot and close a mercury switch. This switch activates an alarm, warning operators of a minor fault so they can take action, such as reducing the load. Now let's look at the operation of the Buchholz relay during a short circuit inside the transformer tank. This is a much more severe fault. A short circuit creates a massive sudden surge of current, leading to a rapid and violent decomposition of the insulating oil. This rapid decomposition generates a huge volume of gas almost instantly. The oil volume expands very quickly, creating a high-pressure wave. This sudden, forceful rush of oil and gas from the transformer tank up towards the conservator, where the Buchholz relay is, activates the lower float of the relay. This lower float is designed to react to this rapid surge. The lower float closes a second set of contacts, which are connected to the main circuit breaker of the transformer. This immediately trips the breaker, disconnecting the transformer from the supply and preventing catastrophic damage or a fire. This is a crucial safety mechanism. Question 10 asks about the function of the power drawn from the supply during a no-load condition. A no-load condition means the secondary winding of the transformer is open-circuited, so no current flows to a load. In this situation, the transformer is still drawing a small amount of power from the supply. This power is necessary to overcome the transformer's internal losses, which are present even with no load. The no-load power, often denoted P0, is almost entirely used to supply the transformer's core losses. These core losses are composed of hysteresis loss, which is the energy lost in the repeated magnetization and demagnetization of the core, and eddy current loss, which we discussed earlier. So, the power drawn at no load is a direct measure of these constant core losses. Let's move on to question 11. Draw and label the circuit diagram of a transformer on no load. For this, we'll draw the equivalent circuit diagram. Let's start with a black background and build the circuit. First, we have the AC supply voltage, which we label V1. It is connected to the primary winding. To the right of that, we show two parallel components. The first is a resistor R0, which represents the core losses, our hysteresis and eddy current losses. The second is a reactor or inductor, X0, which represents the magnetizing reactance. These two components are connected across the primary winding and draw what is called the no-load current, I0. On the secondary side, because it's a no-load condition, it's an open circuit. No load is connected, and therefore no current, I2, flows. We label the induced EMF in the secondary as E2. Following directly from our circuit diagram, question 12 asks us to name the two components of the no-load current. The no-load current, I0, drawn from the supply, is composed of two orthogonal components. The first component is the working or iron loss component. We label this I omega or IW. It is in phase with the applied voltage and is responsible for supplying the constant core losses, P0, in the transformer. It's the component that does the work of overcoming these losses. The second component is the magnetizing component, labeled IMU. It lags the applied voltage by almost 90 degrees. This component is responsible for setting up the main magnetic flux in the core. It does not transfer any real power. The total no-load current is the phasor sum of these two components. I0 equals the square root of I omega squared plus IMU squared. Question 13 asks for the definition of an ideal transformer. An ideal transformer is a theoretical concept. It's a perfect transformer with several simplifying assumptions. In an ideal transformer, we assume it has a lossless core, meaning it has zero hysteresis and zero eddy current losses. We also assume it has zero copper losses in its windings and perfect magnetic coupling between the primary and secondary. There is no leakage flux. In other words, an ideal transformer is a 100% efficient machine that only transforms voltage and current without any power loss. While this isn't ideal, real-world transformers are very close to it, typically having efficiencies over 95%. Two more quick theoretical questions before we dive into the calculations. Question 14. Give another name for transformer ratio. The answer is turns ratio. This ratio tells us how many times the secondary voltage is multiplied or divided by the primary turns. Question 15. What is the stacking factor of a laminated core? The stacking factor, also known as the lamination factor or space factor, is the ratio of the net cross-sectional area of the iron to the gross cross-sectional area of the entire core stack. It accounts for the space taken up by the insulation between laminations. Excellent. We've covered the key theoretical concepts. Now let's tackle the calculations. Question 16 involves calculating the number of turns for both the primary and secondary windings. The key formula we need is the EMF equation of a transformer. The equation is E equals 4.44 times the frequency, times the number of turns, times the maximum flux. It links the induced voltage to the properties of the magnetic circuit. We can rearrange it to solve for the number of turns, N, which equals the EMF, E, divided by 4.44 F, and the maximum flux, Pmax. We're also given that the flux density, Bmax, must not exceed 1.88 Tesla. We can use the relationship that flux equals flux density times the net iron area. And the net area is the gross area times the stacking factor. So our first step is to calculate the maximum flux. We multiply the gross core area, 0.25 by 0.5, by the stacking factor, 0.92, and then by the maximum flux density, 1.88 Tesla. This gives us a maximum flux of 0.065 Weber. Now we can find the primary turns, N1. We use the primary voltage of 2,500 volts and plug our values into the rearranged EMF equation. This calculation gives us approximately 1709 turns. We'll do the same for the secondary turns, N2. We use the secondary voltage of 240 volts and the same frequency and flux. This gives us approximately 164 turns. The primary winding has far more turns than the secondary, which makes sense for a step-down transformer. Let's move on to our final calculation problem, question 17. First, we need to find the secondary no-load terminal voltage. We can use the turns ratio equation, which states that the ratio of the turns is equal to the ratio of the voltages. We have a turns ratio of N1 to N2 equals 15 to 1. This means N1 over N2 equals 15. Since V1 over V2 also equals N1 over N2, we have 1500 over V2 equals 15. Solving for V2, we find the secondary no-load terminal voltage is 100 volts. This is a step-down transformer. Next, in question 17.2, we need to calculate the maximum value of the flux, Pmax. We'll once again use the EMF equation, but this time we'll rearrange it to solve for Pmax. The equation is E equals 4.44 Fn Pmax. We can use either the primary or secondary values. Let's use the primary. We know E1 is 1500 volts, the frequency is 50 Hz, and the number of primary turns N1 is 750. Plugging these values into our rearranged equation, we get 1500 divided by the product of 4.44, 50, and 750. This gives us a maximum flux of approximately 0.009 Weber. The maximum flux is 0.009 Weber. Notice how small this value is, but it's enough to induce the necessary voltages. Finally, for question 17.3, we are asked for the cross-sectional area of the core if the flux density must not exceed 1.25 Tesla. The question asks for the gross cross-sectional area, assuming a stacking factor of 1, as none is given. If a stacking factor were provided, we would use it. The relationship between flux density, and area is phi max equals B max times the area. We can rearrange this to solve for the area A, which equals phi max divided by B max. From the previous calculation, we found the maximum flux, phi max, to be 0.009 Weber. The question specifies a maximum flux density, B max, of 1.25 Tesla. Dividing 0.009 by 1.25, we get a cross-sectional area of 0.072 square meters. A larger area allows for a lower flux density, reducing the core losses. We're almost there. Let's wrap up with the final questions on transformer losses. Question 18 asks us to state whether copper and iron losses are variable or constant. Copper losses, or I²R losses, occur in the windings due to the flow of current. The current flowing through the transformer is not constant. It depends on the load connected to it. Therefore, copper losses are variable losses. They increase with the square of the current, so they are very small at no load and maximum at full load. Iron losses, which are the sum of hysteresis and eddy current losses, occur in the core. The voltage applied to the primary winding and the frequency are constant, which means the magnetic flux in the core is also essentially constant. Because the flux is constant, the iron losses do not change significantly with the load. Hence, iron losses are considered constant losses. Question 19 asks for another name for copper loss. The answer is I²R loss. It's called this because the formula for power dissipated in a resistor is P equals I²R. Finally, question 20 asks where dielectric losses occur. Dielectric losses are caused by the breakdown of insulating materials when subjected to a high alternating electric field. In a transformer, these occur in the insulating oil, the insulating paper and varnish of the windings, and the bushings. These losses contribute to heating and reduce efficiency, especially in high-voltage transformers. And that brings us to the end of our summative assessment walkthrough. We've covered a wide range of electrotechnics N4 topics related to transformers, including construction, safety mechanisms like the Buchholz relay, no-load operation, various losses, and important calculations using the EMF equation. By understanding these concepts and practicing the formulas, you'll be well on your way to mastering this crucial section of your syllabus. Thank you for watching Earthly Teachings. Subscribe for more electrotechnics N4 tutorials and revision lessons to help you succeed in your studies.